So now I want to talk just a little bit more about vectors. And we've talked so far about vectors as displacements. And definitely displacement is the sort of most intuitive of the vectors. But the mathematics we learned for displacements can work for any type of vectors. And so whether we're talking about velocity vectors or acceleration vectors, which we've already encountered, or if we're talking about force vectors or some of the more abstract ones that we're going to talk about in the future, like electric field vectors and magnetic field vectors, the stuff we're going to talk about here today will work for any of them. So let's look at this slide here. So let's say that Becky walked 200 meters northeast of her house. And so we could say then that the displacement of Becky was 200 meters northeast. That's fine, right? That's a fine way of describing this vector. What if Sam, though, walked 200 meters northeast of his farm? And so we have the displacement of Sam is 200 meters northeast. Well, if you compare these two vectors, they have the same magnitude, and they also have the same direction. Same magnitude, same direction. You know what? These are actually the same vectors. They have the same units, the same magnitude, the same direction. They're the same vectors. So we can then say that the displacement of Becky is exactly the same as the displacement of Sam. Now, yeah, Becky started from her house, and Sam started from his farm, but remember, displacement is a change in position. So they can have the same change in position, but start at different places, which means they'll have a different final position, and they have a different initial position, but they can have the same change in position. So that's kind of an important idea there. We can perform what's called scalar multiplication. And to do this, we say, say Sam walked 400 meters northeast and Becky walked 200 meters northeast. Well, these are new vectors, okay? New Sam and Becky vectors. Then we could say that 2 times the displacement of Becky is equal to the displacement of Sam. Notice that 2 is not a vector. It's a scalar, and so we call this scalar multiplication. Multiplying a vector by a positive scalar results in a vector of different magnitude, but the same direction. Multiplying a vector by a negative scalar would actually change the direction. So we can add vectors. We actually already have seen this. We've actually already seen this slide. But we're going to talk about it a little bit more in depth here and a little bit more abstractly. We saw this slide in the context of specifically displacements, and we're going to talk about it a little bit more generally. So vectors always add tip to tail if we're doing the drawing them out technique of adding vectors. So we draw A, we draw B, tip to tail, and then the resultant is C. And the resultant, that's just a fancy name for the sum of 2 or more vectors. Notice that we can add them tip to tail like this, and we get the same resultant as if we add them tip to tail like this. And so, this is not a word you need to memorize, but in math, we say that these commute. And so if B plus A is the same as A plus B, then that means that vector addition is commutative. So, and notice that we get the same thing whether we call B the first vector or A the first vector, right? We still add them tip to tail, and we still come up with the resultant C. And we know that C points in this direction and not sort of the opposite direction, because it always goes from the tail of the first vector to the tip of the second vector. Now we can subtract vectors as well. So here's a list of steps. I'm not actually going to think about it as subtraction. I'm going to think about it as adding the negative of another vector. So we're going to draw A. Here's A. We're going to subtract B from A. How are we going to do that? We're going to draw A. Then we're going to draw B. Okay, great. Now, what we need to do is we need to not deal with B. We need to deal with negative B. So really what we're doing here is we're thinking of this as A minus B. But you know what? I'm actually not doing that. I'm thinking of it as A plus negative B. So that's how I'm imagining this. Well, what does negative B mean? Well, we saw earlier that scalar multiplication by a positive number can change the magnitude of a vector, but not the direction. Multiplying by a negative scalar. Actually flips the vector around. So if we were to multiply b by -1, then we'd have negative b, which is the same as b, but in the opposite direction. So instead of thinking of this as a minus b, I'm going to think about it as a plus negative b. And I already know how to add vectors. I simply do them tip to tail. I place my first vector down. My second vector goes tip to tail with my first, and the resultant goes from the tail of the first to the tip of the second. And that is a minus b. One place where we have seen vector subtraction coming in is in acceleration, right? Remember that acceleration is a vector. And remember that an acceleration vector is equal to a change in velocity over a change in time. Well, what is a change in velocity? Well, change in anything, right, is v final minus v initial. So, if we're talking v final minus v initial, we're talking vector subtraction. So, looking here, what if we've got some v initial here and some v final here? Now, we need to be careful with these velocity vectors, actually. We see these vectors and we think of them as having some spatial extent, right? But if I'm talking about a particle right here, and I tell you that its velocity is over here, let's say, what do I mean by that? I don't mean that the particle is moving necessarily from here to here, right? What I mean is that at this exact point, his velocity is represented by this arrow. In other words, the length of this arrow represents the magnitude, and the direction represents, well, the direction of the velocity at this point, right? And so, in order to draw arrows, these arrows have to have some spatial extent. But let's be clear, there is no spatial extent to the velocity vector, right? The velocity vector itself, the idea that it represents, right? That there's a spatial extent to the drawing, right? But the idea that it represents, there is no spatial extent to that. It is just the velocity at a single point in space. It is the velocity right here. And typically, when we draw these things, we let the vector that we're drawing, we let it represent the value of that vector at the location of the tail. And that'll be more important when we start talking about forces. Okay, so again then, to see what we're looking at here, this is the initial velocity. So this would be the velocity of the particle when it's right here at this point. And this is the velocity of the particle when it's right here at this point. So now we draw velocity final. And now, instead of thinking of this as minus v initial, I'm going to think about it as plus negative v initial, right? So I take my v initial, I flip it around like that, and then my delta v goes from the tail of the first to the tip of the second. Delta v is equal to v final plus negative v initial. Now we know that since delta t is a scalar, delta v is a vector, a is a vector, since delta t has no direction associated with it. The direction of a must be the same as the direction of delta v, and therefore we have found, by finding the direction of delta v, we have found the direction of a. Okay, why don't you try one? So which vectors below represents the vector sum p plus q? Try it on your own. I'll see you on the other side. Okay, well notice that the way they've drawn them here is not really the way that we've been shown to do this, right? We really need to do it tip to tail. So what I'm going to do is I'm going to draw my P here. So right now I've kind of got Q, in the PowerPoint I've got Q drawn right here, right? But that doesn't help me, right? Because these are not tip to tail, these are tail to tail. And so the way we're learning here today is tip to tail. We're drawing them tip to tail. So we're going to take Q, we're going to move it from here up to here. Something like that. So now we have P plus Q. My resultant goes from the tail of the first to the tip of the second. And there we have P plus Q. And PowerPoint agrees. Okay. Let's try another one. So which choice best represents P minus Q? Give it a shot. I'll see you on the other side. Okay, so now I've drawn P. Of course, I've got Q here. But what I really want to do is I want to add negative Q, right? So I'm going to think of this not as P minus Q, but rather as P plus negative Q. So a minute ago I had Q right here. Well, if Q was right here, then negative Q must be right here. And to avoid confusion, I will now erase Q. Okay, so there we go. P negative Q. The resultant goes from the tail of the first to the tip of the second. And there we have P minus Q. Great. Let's try one more. The diagram below shows two successive positions of a particle. It's a segment of a full motion diagram. Which of the acceleration vectors best represents the acceleration between VI and VF? VI and VF have the same magnitude. Okay, so in other words, the length of this arrow is the same as the length of this arrow. So which of these choices best represents the acceleration vector at this point right here? Okay, give it a shot. See you on the other side. Okay, so here I've drawn my V initial and my V final. Recall that since the acceleration is equal to delta V over delta T, then we're looking for V final minus V initial for the direction. Again, as I said a moment ago, since delta T has no directional component to it, there's no, right, delta T is not a vector, it's a scalar. The only direction here is in delta V, which means that A must have the same direction as delta V. So we're going to find the direction of delta V, and then that's going to tell us what the direction of A is. And V final minus V initial will give us delta V. Once again, I'm not going to think about it as that. I'm going to think about it as V final plus negative V initial. So what does negative V initial look like? Just like that, but upside down, something like this. There's negative V initial. And so what does my resultant look like? Something like that. That's delta V, and therefore the same as the direction of A. They're not the same vector, but that is the same direction. They don't have the same magnitude, right? A and delta V don't have the same magnitude because delta T is a scalar. It'll change the magnitude, but it does have the same direction. So D is our best choice. There it is. A lot of times when I do this example, students will say, well, why isn't it C? Wouldn't C work too? Well, you might get C with a slightly less than perfect drawing, but notice that it can't be that if these two are the same length, right? So if these two vectors are the same length, then they're not going to end up with a straight line here. This is going to be a little bit below. Okay. Okay, so let's talk a little bit about components and vectors, and we've done a bit of this already, but it's been in terms of displacements and east, west, north, south. And so now we're going to add a level of abstraction to it here. We're going to put this in the xy plane, and this is a vector, I don't know, let's call it B, vector B. Sure, looks great. So vector B points over yonder, and we can we call this finding the components of vector B, or resolving it into its components. And so you can see here that the y component is here and the x component is here. Notice that since B is sort of pointing more up-ish than down-ish, then y, the y component is positive. Since B is pointing more to the left-ish than to the right-ish, the x component is to the left, or in the negative direction. And, you know, this makes it sound much harder than it is. The absolute value, a sub x, of the x component of a sub x is the magnitude of the component vector a. Oh, goodness gracious. Basically what this is saying is that the x component has a magnitude of 2 meters, as we can see from this drawing, and the y component has a magnitude of 2 meters also. Right? And so the components have those magnitudes, right? And x or y, yeah, again, this is all 100% correct. It just makes it sound more confusing than it is. I feel like the picture really describes it nicely. Let's just practice a little bit. What are the x and y components of this vector? Give it a shot. I'll see you on the other side. All right, so there I've written my vector. I've drawn my vector. And so what are the x and the y components here? Well, my x component is 2, and my y component is 2 and 3. Now, notice here that I haven't told you what this vector is. It might be displacement. It might be an electric field. And so then we've got an electric field that's pointing a little bit in the x and a little bit in the y. Okay. Again, we found the x and y components of the vector. How about this one? Here we see that this vector is kind of pointing down and to the right. And looking at this, it looks like it comes out to what? About, it comes out to about 3, doesn't it, on the x-axis, right? So we can imagine a light that was shining here. And if it was shining directly in the positive y direction, then the shadow of that light on the x-axis would sort of tell us the x component. So I think we've got an x component of 3 and a y component of what? 1, 2, 3, 4, negative 4. So here we've got an x component of 3 and a y component of negative 4. Here's one. The length of vector b is 4 units. Again, we don't know what it is. Later on, next semester, you'll see that we use b to represent magnetic fields. Magnetic fields is a vector. So maybe this is a magnetic field vector that's pointing sort of in the positive y direction and sort of in the negative x direction. Okay, well, can we find the x and y components of this magnetic field vector? I think we can. Let's see. And this is 30 degrees. Okay, so what we want to do is we want to turn this into a right triangle. We've got our 30-degree angle there. So then our right triangle looks like this. And notice we're really doing vector addition here. We really are, right? So what we're really saying is that b sub y plus b sub x, I can drop the vector sign if I'm in one direction. So this is in the y, that's in the x, right? So we could say that b sub y plus b sub x equals b. We could say that. We are doing vector addition. But more specifically, we're finding the components of b. Okay, so don't forget your SOHCAHTOA, right? If I'm finding b sub x, then b sub x is the opposite to this 30-degree angle. I know the hypotenuse, and so opposite and hypotenuse, that is sine, right? So we should write then sine of 30 equals opposite b sub x over hypotenuse b. And you can see here that we can now just do some algebra. Which means that 4 units, whatever those are. And the sine of 30, well, one way we can get the sine of 30 is just run our calculator, right? Totally works. Works every time, unless you're in radian mode. But those of you that might be taking the MCAT in the near future should know that the sine of 30 is 1/2. Again, your calculator will tell you that. And so b sub x must be 2. All right, how about the y component? Ooh, wait a minute. We need to be a little bit careful, don't we? B sub x is 2, but let's go ahead and let's not quite put a final answer around that box. Huh? So we got that the absolute value of b sub x is 2, didn't we? But notice that it is pointing in the negative direction. And so we really should have b sub x equals negative 2. Again, your SOHCAHTOA is not going to tell you that. Now let's look at the y direction. The y direction is adjacent. So adjacent and hypotenuse. Which trig function is that? If you said cosine, you are completely correct. And so we should write that b cosine of 30 equals b sub y. And I suppose to be completely correct, we should include some absolute value signs there. Although, you can see that our y component is going to be positive. And so we should write then that b So we should write then 4 units times cosine of 30, square root of 3 over 2. Again, your calculator will tell you that. You don't need to memorize it unless you're planning on taking the MCAT. And so we run our calculator and we get 3.5. And so those are our two components. So we could write negative 2, comma, 3.5 as our final